I guess in any case, welcome to our second controls workshop. This one's going to be a lot more examples and whatnot. To start off, I'm going to check my notes real quick. Ooh. So to start off, I just wanted to do an example of linearization. I know I want to set up like drawing pad that I had, but that wasn't working very well. So we're in Word now. But essentially, I want to give a example of linearizing a function. So if you recall linearizing from the last week. Oh, I'm not even sharing my screen. One moment. I'm like pulling up the slides on my screen, but no one can see them. All right. There you go. You can see that now.
Yeah, I can see it now.
All right. So what I'm going to do is I have a nice function here that I want to linearize. And sine, cosine, trigonometric functions, those aren't linear. I'm sure as you know, both of them oscillate. They're very much not a line. And usually if our system dynamics would probably be more complicated than this, but for this example, this is fine enough. And for this example, let's say I just want to linearize about x star equals pi. So to start off, I'm just going to kind of go through, and we have f of x star delta. And so the first thing in our equation is literally just f of x star, I should say. So we put this in, but now we put in our values for x star, which in this case is pi. Actually, just to make this a little bit more different, I'm going to change this to pi to pi. Keep things a little bit interesting. That's basically just substitution. And then, we have our second part, which is, plus our delta x. That's basically delta x. You can think of as how far off we are from the linearization point. So if I was, for example, can I draw? Is that legal? Oh, whatever. As I move further away from the delta x increases, and then, it can obviously also be -2 depending on what direction you're going. Basically, it's just telling you how far along this line you are. But that is multiplied by df dx. And so we can take the derivative of f of x, which for trigonometric functions is pretty easy. This becomes cosine of x of 1, and this becomes minus sine x of 2. And with that, it was a relatively simple example, but now our function is linearized. This is a line that approximates our function about the point x star equals pi over 2 pi. So, the further away we get from that point, the less accurate our system is. But this example makes sense. Or do you have any other questions about linearization before we go on?
No, it's really simple.
All right. Yeah, I didn't want to spend too long on it since it isn't that complicated. All right. So next, pull up paint. We're gonna do some dynamics. So what I want to do is basically kind of go through a simple example of a particle in motion and how we can find the find the dynamics for it. So if I have, I guess for this example, we'll have a nice car. I'll draw using my excellent art skills. Oh, it's a pickup truck now. Okay. In any case, what we're going to do is basically make a free body diagram of this. And I'm going to make this very simple. We have the center of mass and just one force on it, F. And for what we're doing, we're going to have F. And to make this really simple, F is just going to scale linearly with time. So for every 1 second you go, that's an additional Newton of force. So, this is pretty simple to do. The first thing, though, is if we want to go about figuring out how the actual system moves, is we need to find, well, the, what's it called? We need to find the acceleration. So I'm sure you know what that would be. You know what it is?
It'd be force over mass.
Yep.
So T over M.
Yeah. I guess technically that should be F of T, but whatever. But yeah, so this is a good, this should be able to get us the actual answer. And I guess just for this example, I'm just going to go to velocity. So if we want to know the velocity of the truck over time, what would that then be?
T squared over 2M plus C.
Correct. And then, I guess
We
T
assume it
squared
starts at
over
rest, so
2m.
C is 0.
And yeah, then I'm going to have the initial conditions of the truck, basically
Starts at 0 and
V of 0 equals 0. And then for now, we're not bothering with the position, not for this example. Yeah. So now, if we want to, we can just straight graph this, and that'll give us a nice answer. It's very nice analytical, but I'm going to make it harder, and we're instead going to use this as an example and compute it numerically. So I have already done a little bit of work here. So where you go into Matlab, we have, as I mentioned earlier, f of t equals t, and we have our analytical solution there. And have you ever used fplot before?
No. Does it just plot a function?
Yeah, it just plots a function. And basically, I guess another quick thing, have you ever used an anonymous function before that's basically this at syntax?
No, I'm not familiar with that.
Mini lesson. So, the traditional way to define a function would be function x equals, func, and then you do your, whatever's in there. Like, I guess in this case, we just have x squared over 2m, whatever. But because this is only one line, we can write this much more compactly, as I did up here, where you basically do at parentheses x x squared over 2m, and this is basically shorthand for just making a function on the fly. And you could do things too, like if I want to just assign this to a variable, I can just go like that. And now anywhere I want, I can call func just like any other function. I could do func of 2, and that, if I run this, gives me 2 squared over 2m. And I guess also just for the sake of just fully understanding how anonymous functions work, you can have more than one variable. So it's pretty simple. Basically, it's called an anonymous function because the function doesn't. You're basically creating a function without a name. I think that's the idea. I might have that slightly wrong. But this is
For
excellent.
fplot, you just like put the intervals from 0 to 5, but it seems like it's not really creating like an array for like the. You know how like usually when you want to plot something, you first create the vector and then you for like the x variable, and then you create another vector for the y variable, and then you plot those against each other. It seems like fplot doesn't really do that. So does it kind of like find the value at every single x?
So, actually, what I will do real quick, if I change the style of this line to just dots, oh, if I get the syntax correctly, you'll see basically what fplot is doing is it's taking the point at intervals along the line. So this is the same as if I were to go like y equals func of, and then some range like 0, 0.1, 5. And then I were to just plot that. I think I can.
Does it just decide the intervals on its own?
Yeah. So basically, fplot is basically just a way of kind of doing. It basically does a bit of the work for you, kind of behind the scenes in terms of just calculating all the points. Essentially, all it does is it takes your time interval and just spaces out points along the time interval, and just for every point in that interval, it applies the function you provided. And there's also a like 3D version of this too. Does that kind of make sense?
Yeah,
Okay.
makes sense.
It's a relatively simple thing, but it can make your code a little bit more readable and a little less verbose. But yeah. So in any case, we have our nice analytical solution here that we found. And what we want to do is, basically apply the, if you remember from last time, the numerical solutions we were talking about with the differential equation solvers. Do you remember that?
Yes.
So what we're going to do is use MATLAB's ODE 45. And actually, this was something Troy pointed out to me. ODE 45 is apparently not actually based off of RKF 45. I got that wrong from a thing I read. That I think it was. Let me just. I'll figure out what it really is. It's RKDP. I'm sure you can Google that if you care. Okay. Well, in any case, on to OD45. Essentially, OD45, the end goal is we want to know velocity. So what we're going to do is we're going to provide acceleration and just skip the step of doing the integration by hand. And, obviously in this case, it's overkill since it's literally just power rule. But in the case that you can't integrate it, this is a lot more helpful. So the arguments for ODE45, the first thing is the ODE function. And it's basically a function for what we're integrating. And I'm just going to do the same thing I did up there for fplot, where I'm going to create an anonymous function. And this time our argument is t. We're basically just taking the time since it's time dependent. And it's very simply t over m, just that a equation. The t span, I'm going to use the same span as the other one. And then we need the y naught, basically the initial value for the function, which, as I specified earlier, is just v of 0 equals 0. And then you can provide additional options, but that's an optional thing. You don't have to deal with that. That's useful for later on when you want to modify how the function works. Change things like the accuracy of the function and other such things. You can change how it handles time steps. But in any case, what this will do is OD45 returns two variables. it returns t and it returns y. I guess in this case it's x. The documentation says y though. And you can see I already have a plot x of t and y. T should be on the x-axis. And yeah, so with that.
Wait, what is x? Isn't
So,
that velocity?
oh, actually, yeah, you're right. I should be more specific. It is v in this case.
Okay.
And I apparently did something wrong. Too many input arguments. Well, this is D arguments. I'm sorry about this. Did I mess something up somehow? All right. Quick side lesson. It's very, very nice to always visit the OD45 documentation. Because OD45 is one of the much more popular functions in Matlab, there tends to be a lot more just stuff on it. So here's a similar example that they give. 2 times 2. That's odd. Oh, I'm an idiot. Okay, so this is a good thing to learn. So when you're this was a silly mistake on my part, but this is something that's very easy to make if you are using OD45 for the first time. Whenever OD45 calls your anonymous function, it always provides 2 arguments. It provides t and it provides y. So you have to accept the argument y, even if you're not using it. And vice versa, you might have to accept t and only use y. But basically, this is just like the standard type of function that OD45 expects. And another quick thing, oftentimes you might, actually, let me just run this. Oh, I forgot to suppress those. But as you can see, the numerical solution perfectly matches the analytical solution. It basically just covers it over. So even though the numerical solution is an estimate, it's a really good estimate. Do you have any questions about just this basic OD45 stuff before we move on?
Referring back to what we talked about last time.
Yes.
So you have like a set, like a vector that describes like its motion, let's say for a particle. But then we know like x dot, and then we could use like OD45 to like go back to the regular x.
Yes.
But in this case, it's just like a simple particle moving in one direction.
Yeah. So you can. It probably does help to think of this as like x dot and whatnot. This f right here is basically our x dot. Actually, more accurately, this is our x dot. The a of t is how our velocity changes. In this case, we just have a one-dimensional system. There's only one state variable, which is velocity. So x dot is how x changes. In the future, we're going to have more different variables.
Does ODE, is it able to solve it when as the vector has multiple components?
Yeah, so let's actually make this example a little bit more complicated, and we will add, position. And for us, position is the integral of velocity over time. And this is another thing we'll get to. Now that our, system is getting a little bit more complicated, I could write this anonymous function, but what I'm actually going to do is expand this out into a regular function, just to kind of demonstrate what that's like. So I have our function, and basically what this needs to do is return x dot, how the system changes. And this is equal to and remember, because what we're going to be doing is putting this into OD45, it must take t and y in that order. And so what we could do in here now is we have to return x dot, and x dot will be, that has to be position and velocity. And a quick side note, x dot and your x is required that it's a column vector. That's just how OD45 works. It only works on column vectors. So what we could do now, we now know that, well, just quickly for velocity.
Just a second right there. Isn't so if x dot is a vector with components position and velocity, then what is x?
So, oh, okay, actually you're right. This should be p dot v dot.
Okay.
That, I'm glad you caught that. But okay. So we know v dot already. V dot equals 2 over m. And as a quick thing right here, m, because we're now within this function, we now don't have m in our local scope anymore. So what I'm going to do right now is just add it as a input argument. And you could go ahead and add m as a global variable, like global m. But I personally like to avoid that just because global variables tend to invite bad things just happening. It's very easy to lose track of global variables and things just break. So if you're doing something like short and simple like this, global variables are fine, but I want to teach you the more safe way to do it, I guess. So what I'm going to be doing is providing m as a input argument for the function. Sometimes also too, if I have something really complicated, I might get into object-oriented programming and pass in like a class or something, but that's for another course. But in any case, we'll now go into finding p dot, and we know that p dot is essentially, we know for a fact that equals the velocity, right? So what we can do is, now this is why y is also passed in here. We can just take y of 2, and that is just the velocity. There's nothing fancy that we have to do. It's all set. Okay, it's just getting mad that I'm not using it.
What's y of 2?
So y of 2, if we, go and look at, just let's make a y naught. Why not? I guess I'm going to keep it as x just so it's consistent. The OD45 documentation uses y, so it's kind of sticking to that, but I very much prefer x. So the initial conditions, let's say that it starts at 3 meters ahead from wherever 0 is. It's starting, ahead of a line, I guess. And as earlier, it has 0, the velocity, it starts from rest at 0. What I'm referring to here is, when I say x of 2, that's the second element of the state. In this case, our initial state here, position second is velocity. So basically what this is doing is this is just taking the state and just returning the second part of it, the velocity. Does that make sense?
Yeah. I guess the format was just unfamiliar.
Yeah.
It seemed like it was like a function.
No, yeah, see, this is another thing that I am not a fan of the Matlab syntax on. In something like Python, the syntax for indexing an array and calling a function are distinct. Like in Python, you do that, but it's less obvious in Matlab. Um, but okay. So in any case, now this we have equations for p dot, v dot, and x dot, and I could write this up much more compactly and just put these in there. I could probably even write this whole thing as an anonymous function since it isn't that big. But really, my goal here is to kind of get used to the general style in which these things get written. Um, so now, if we go back to here, I'm actually so what I could do is do system dynamics. And this is doing something like this. This basically, this at basically gets you the variable at, or sorry, it gets you the function as a variable basically, which allows you to pass it to things. It's basically giving a reference to the function, so that OD45 can call it inside. Um, but the problem with this is that when OD45 goes to call this function, what it's going to do is try, if I just run it, you'll see we get the same error as earlier because, actually, there's a slightly different error, I think. Um, because we're calling, OD45 is calling this with the arguments tx, but we also have a third one. So what I'm going to do is instead do system dynamics and back as an anonymous function, and this takes txm. And basically what this is saying is it's an anonymous function that takes t and x, and then it's just passing that straight to the system dynamics function with t, x, and then this m, because we're back in the outside scope, it can take the m from here. Does that make sense?
Yeah.
And now, if we change this to x, and now because we have more than one thing, we can plot both states. So let's be a little bit specific. This one is the position. This is velocity. Oh, and it's still broken. What's going on? Oh, okay. So I skipped a step here because I left our initial x as just 0 when I forgot to do x naught. So basically, that's just taken from there. There we go. Velocity. Where's my position? Did it just... There's something going on here. Oh, I need to not have hold on. That's my problem. My bad. There we go. And it's... I'm sorry about this. I'm not sure what's going on. So let's do some debugging and go and look at our X. 41 by 2 double. And basically, this is a record right here of all, it's basically a record of the variables over time. So you can see this first column, this is the first state position, and this column is the second state velocity. You can see it varies over time. And the way OD45 works is it perfectly matches the t vector here. So you can then just plot t versus x, and it gets you a nice result. When it works, though. I'm not sure what's going on here. Oh, I'm bad at indexing. I've been writing a lot of Python recently, so I'm still like in Python mode. Oh wait, it's all rows, one column. Okay. God damn it. I'm sorry about this. There we go. Okay, finally. So we can see the velocity over time and the position over time. You can see this goes up quite a bit more. So does the vector way of doing this make sense?
Yeah.
Great.
Would you be able to make force a vector function so that the product moves in 2 dimensions or more?
Yeah, so that's basically, kind of the next step up, where now instead of this is basically a one-dimensional problem. If we go back to our thing, in essence, this is just a uh, particle moving along a line and whatnot. It just has P and V. Basically, as you were just saying, the next step is, a particle. It's now moving along a plane, and it can move in 2 dimensions. And now P and V, it still has both of those, but now they're both vectors. There's a P1, P2, and a V1, V2. And sometimes depending on the application, there's different ways to do this too. If you wanted to, you could have P1, or you could have like a PX and PY, basically your XY coordinates, and a velocity and then a heading angle, which basically says, what angle is the velocity pointing at. And that's something that's used, oftentimes when we're doing things like modeling an airplane, because, it's convenient to track heading angle. It depends on what kind of problem you're solving, what the most convenient way to do it is. All right. So I think what we're going to do now is we'll have a example, which actually, you know what? Why don't we so do you want to go ahead and launch Matlab?
Sure.
Yeah, so I think what we'll do is have a nice trying to think. So we'll consider the system dynamics of this block basically just moving in a 2D plane. And what we're going to have here, well, a force downwards, and then a force like that. Then this force will just be a constant Fg. That's our gravity. There's a reason I'm not an art student. And this is just mg And we'll give this value, let's just do the same thing as earlier, where this is ft, and it's acting at a 45-degree angle. So we're getting a little more complicated here. Now there's forces in two directions.
Could be, I'm not sure if it's too complicated, but could we make the angle a function as well?
Yeah, if we want to. Well, might as well. I got nowhere better to be tonight.
You can make it like a trig function so it oscillates.
This will equal the absolute value of sine t. There we go. That's exciting. Okay, well, now I've got no clue how this will move. I'm sure it will be very exciting. So with this, I guess we need some initial conditions. So yeah, let's just that'll just be 3. I guess so now theta, because that's something we need to keep track of.
Wait, theta, it's only going to oscillate from 0 to 1. Is that what you wanted to?
Yeah, I was just thinking.
It pretty much just goes in circles, I think.
Well, so 0 to 1, that'd be 0 to 1 radians.
0 to 1.
So that's like between straight across the x-axis and up here. I mean, if you have a preferred way to vary theta, I'm happy to let you derive it.
No.
Okay. So, well, let's do our x naught. So x naught. So, give her a vector, and we have, our x and our y. So we have px, py, and then we have vx, vy. But also, because we have this theta, that's something that changes over time. We now have theta as a variable, as a part of our state. I drew this a little too close. Let's. This is x of t. And we'll do our x naught. Px we'll just have as 0. Py we'll start it a little high in the air. 10. Vx will set velocity equal to just 0 and 0 initial angle. So that's our initial state vector. And okay, with that, I don't think there's anything else I need to set up for this problem. So what I'm going to do now, I'm going to stop for a moment and take a picture of this and throw into Slack. And I'm going to stop sharing so you can try this out for yourself. Controls Workshop is way up here. I'm sure everyone would love my artistry. So let me cancel my screen share. And then do you want to go ahead and share your screen so I can kind of work through it with you?
Yeah, I can do that.
Great. So I guess I'll let you go at it now, and feel free to ask whatever questions.
Okay. I mean, I followed you, like, I was able to follow what you were doing when you tried it, but now that I'm on my own, I'm completely clueless. But
yeah, so if you want, I can send the file that I was just in Slack too, so that you can open it for reference.
That'd be great.
Yeah. You give me a moment. Uh, it's a live script. Very fancy. Oh, Matlab's being all weird. There you go. You see that?
Yes, I do.
Yeah. What we're doing right now, this is, I think, probably the most important. Like, just if you're gonna get really good at just one thing for doing before we get into like the cooler stuff later on, I think this is probably the most important basic skill right here. Which I think, you know, yeah, because we can't control a system unless we can actually predict what is going on.
Mm-hmm. Okay. Let's see. Also, what I didn't understand was what these little boxes were.
What boxes?
Um, One's right here.
Oh, that's just formatting. That doesn't mean anything syntactically. Um, have you ever used a live script before?
Not really. I mean, I have, but I don't really know what the difference is from live script and like a regular script.
So think of a regular script as just straight code. It is code. It executes by itself. Live scripts is basically fancy code in the sense that it behaves almost exactly the same way as your regular code, except for live scripts, you can dress your code up a little bit and put in write things right in your code. So you can see I did that up at the top. Because it's a live script, I can type equations out in it. Um, and you can also type I could put in like a paragraph or something there.
Mm-hmm.
Um, and that doesn't change the code, but basically it lets you write about the code right in the document the code is in. And it's useful for if you're doing something like homework, you can do it in a live script where you have the start of your problem, put in what the problem is, and then give an explanation of your problem, and then the code is just right there beneath it.
Yes.
Yeah. And there's some other features too, like you're able to run particular sections of a live script. But that's the gist. It's basically a way to combine a Word doc with code, in
Okay.
essence.
Yeah. So this was essentially doing it by just like integrating.
Yeah.
But
So,
we're
well,
not going to be
actually,
doing that.
not that X not. I guess the X
Oh,
not I should have
okay.
put below the comment.
But this part was without using OD45.
Yeah. So that's just using the analytical solution. And I mean, I haven't checked. There could be an analytical solution to the problem, but it's probably a reasonable amount of work to find.
Right.
And I'm too lazy to do it. So,
So we're going to do something like this.
yeah. So first we got to kind of, go and basically work through the state vector and find an equation for the derivative of each state.
Okay.
Um,
Um, so we have x as x position, y position, x velocity, y velocity. So do I want to like write out what x dot would be?
yeah.
Maybe if I create a live script, I can just type up some equations just so it'd be easy to look
Yeah,
at.
that's a good idea.
Okay.
I'm also realizing that the way we handle theta might have to be different, but when we get there, I'll talk a bit more about that.
Okay. Um, so x.
So if you want to get the nice equation, you go to insert up on the top,
Yes.
equation on the right.
Okay.
And then you get your nice fancy LaTeX flavored equations.
I create a vector.
Yep, you can make vectors. I think it's a different tab. Do you want to close that real quick?
Yeah.
Matrices on the far right.
Okay. So
you have to click the drop down on that to then create a matrix of the size you want.
yeah, that would make sense. Okay.
Drop downs within drop downs.
Like this big, yeah. And then I'll do, then is there like a shorthand?
I think you can type \theta and then hit space.
I don't know why you created another cell. Oh wait, you created a fraction. Never
Yeah,
mind.
it's a fraction. That's what's going on.
\theta. Okay.
There you go.
In that case, and then I know that is it just \x dot?
I think you have to do \dot space x. There you go. Oh, but you have to leave the cell that the dot is out of, otherwise the dot just keeps extending across the screen. I gotta say the MATLAB equation editor definitely isn't as good as the Word one.
Yeah. And then there's there's gonna be a lot of dots.
Yeah, so let's start off with the easy ones. How does px change?
Is it kind of just like put v instead of p dot?
Yeah, so here, rather than writing, just p dot whatever, we want the full equation for it.
Oh, the actual equation.
Yeah.
Well, this is equal to, we know that we don't know. So this we don't know yet.
Yeah, so
we'll leave it like that.
yeah. So here's the nice thing about doing this is we can reference the state, the current state in the state vector, because while we don't have an explicit equation for v, we have the we have our approximation of v at the current time.
Right. Yes.
And essentially, all this exercise is doing is saying we can pick any arbitrary point within the state space, and then it will tell us if you're right at this point, how will it change? And we don't necessarily need to know how we got there. Maybe that's the initial state, but yeah.
Yeah. Okay. And force is a function of t. So
yeah. So now
this
is going to be
cosine theta.
well. So this is going to get a little bit more. Oh, actually, no. I see what you're doing.
Is that it? And over m. Oh. Am I in the right?
What equation I had? So. Okay, so we have the current. Yeah, cosine of theta gets you the x component. T is the. I think that's right.
Yeah. I think so.
Yeah, so it's a over m. Yeah, okay, that looks good.
And this is just theta.
So real quick, you also can't forget about the other force, Fg. And that acts vertically.
This minus mg.
Correct.
This...
So actually, now that we're to theta, I'm realizing I'm not sure that is there a convenient way to find the derivative of an absolute value function?
No.
I'm thinking for this example.
Unless I can go into Symbolab and see if it gives me a solution.
No, actually, let me do that right now. I got Symbolab open.
Absolutely.
Derivative of sine of x.
But
what is it?
Value.
Oh, this is interesting. Uh, so the derivative of the absolute value of sine of x is sine x times cosine x over the absolute value of sine x.
Yes.
That's interesting. I didn't know there was an
I'm
easy
curious
equation
how
for
they
it.
figured that out, but whatever.
Oh, it's a chain rule.
I'm thinking that too as well. They just pulled out a sine x over absolute value of
Oh,
sine
that's
x.
funky. Okay. Well, okay, in that case, yeah, we don't have to change the problem.
We can try that then. So theta will just be
So
that.
it's sine of theta. Oh wait,
Sine of
sorry,
theta.
what was
Yeah.
it? Oh, our thing is sine. Sorry, it's sine t because that's what our variable is.
Sine t.
Yeah, so this equals theta, but with it's the absolute value. So theta is equal to the absolute value of sine t. That's what I ended
Ah,
up finding.
right.
Yeah,
Because theta is a function of t.
yeah,
Yes.
theta is time dependent. Ooh, I'm liking this example. This was a good idea.
Is there a thing for absolute value?
Yeah, it goes over absolute value. So that's just the where the pipe key is. Oh yeah, there you go.
Is it sine? Yes,
Yeah,
sine
sine.
t. Oh wait,
All
so
right.
this is also not. Wait, no. This should
Yeah, so
convert
those
to
ones, those are actually sine of theta. So
right.
basically
But do
what
we
we have
want it to
here
convert it
is
to a t though?
no, so what we
No,
have
we
here is
don't
good
know.
because
No, we do know.
essentially what's going on here is the last element in our state vector that changes depending on only t. Um, but then we have our two middle ones. Those depend on theta, which is the
Right.
last element, which we know at any given time, as well as the current time,
Okay.
as well as m.
No, so what I was saying is we not want to write data as a function of time?
I'm you can write theta of t. Usually, if it's states, I usually just go with like
No, as
I,
as in like put in like instead of theta put in like absolute value sine of t.
no. So because I think you could, but I think at least for this example, um, I'd like to stick with what I have here because basically what we're doing is we're using our estimate for theta because as you see, we have it as that last thing in the state vector.
Okay.
So okay, I think with that, I think we're ready to. We have everything we need, so now we can start coding.
Okay. Well, so first I could put in. Wait, I might. Is the editor right now?
Yeah, so to
Okay.
get back to the code, you have to go to, it's in the live editor tab, live editor tab on the top, and you just click code, and that changes there you go,
There we go.
and makes
So
a new block for you.
okay. So I can first just create the initial
Yeah.
x naught.
Oh, and remember this has to be a column vector. Right now you're making a row vector.
Would that be like this?
Yep, that's column vector.
Okay. Um. Then let's see what you have here.
So we also need to define m because that's important.
M. Right. Okay. M can just be
Actually,
one.
real quick, let's actually not define M right here because I'm going to show you another way of doing that that's very slightly different that you might prefer.
Okay. So
Um,
ODE 45 only outputs two variables.
yes.
How would
So
that work in our case if we have so many different components?
so basically what's happening is it's outputting two variables, but one of those variables is a matrix. So
Oh,
if you want to just run this real quick and just look at the variables again, you'll see that t is a vector that's the time vector. It has the like time at every step in our simulation.
But X is a matrix.
And X, you want to go ahead and open X up?
Yes. I see.
X matches up with that T vector. So
Each
each column is a
column is
different
its own
state.
vector.
Yeah.
Got it.
So think of it as the, X1 then X2 vector.
Okay. So it may look like it's outputting two vectors, but really it's a vector and a
Yeah,
matrix, so multiple vectors.
that's correct. So
Okay.
that X has a big bulk of the data we're finding.
Okay. And you're able to put the function into this program through this system dynamics thing.
Yeah.
And that's here. Also, I'm not too familiar with using functions in MATLAB.
Oh, okay. I guess just to go over basically what the function does. Functions is just a way of creating nice, repeatably executable code. Essentially, a function takes some number of arguments that you specify, and then it executes whatever code is inside the function, and then returns the return variable. So in this case, we specify x dot is the variable returning. So whenever the function hits that end at the end of the function, whatever thing is there for x dot is basically just returned from the function. So you can kind of think of whenever you
So
write a
x dot is
function.
the output of the function.
Yes, that's correct. So basically, whenever you're putting in a function, imagine that as it's the actual output of the function is just replacing the function itself in your code.
Okay. And then system dynamics, is that just the name of
Yeah,
your
so
function?
that's just a name. You can change that to whatever you want. You might want to call it, you know, state derivative or something. I don't know.
Is this like this part actually contributing to the code, or is it
Yeah,
just
so that part right there, that tells your function what
what the inputs
arguments it
are?
takes. It tells you what the inputs are.
Okay.
They're often called the arguments too.
Okay.
Um, and it always takes them in that order. So if you see the state dynamics up there, I give
Oh,
the
I
arguments
see.
in that same
So
order.
this x dot is a vector function essentially
Yeah,
that
so
takes t, x, and m and puts it into it. What
yeah, so
once it after
basically
puts into this.
we can kind of think of the function as a black box that we give it three variables and then it returns a too long
It's
vector.
yes, but like in this part of code, it's not actually inputting anything. It's just defining it, right?
Yeah, so you can kind of think of it as a self-contained script. Once you're in the function, nothing outside the function affects the code in there, and nothing in the code in the function affects the outside code.
Okay. So
At least for the most part in most functions.
okay. So I should start by creating that function and like
Yeah.
telling it what x dot is equal to. Um. So x dot. Okay. I'll try using the function that I've done before. Function of x dot is equal to.
And just another, side note here, functions are useful for a lot more than just, using OD45. If you have, some equation that you use many times in your code, even if you're just doing like, something like astronautics where it's just a lot of algebra,
mhm.
and there's a particular equation you use a lot, rather than writing it out every time, you can instead make a function that does it for you. And then now you don't need to write out like, your whole huge like let's say you're calculating like a rotation matrix. It's just algebra to find that, but you can shorten it by rather than pasting this huge matrix definition everywhere, you essentially just have it calculated within a function, and then the function just returns your matrix. You
Okay.
only need to write the code once, and it prevents you from messing things up when you type it out multiple times, and it shortens your code a lot.
Mhm.
All right. So in this case, let's only do t and x.
What is x?
So x, that's our state vector.
Yeah. Okay. Okay. Yep.
So basically the state vector at the current moment in time. And
Okay.
then for now, don't put m there and just hit end. And
Assign. those.
Yeah. So before we do that, let's define m here. So basically inside the function. I think in our example, m is 5. It was.
We gave m a value. Oh, it's
M equals 3.
Okay. Do I have to put the semicolons inside of the function?
Yes. So
Okay.
you know what the semicolon does, right?
It like pretty much ends it, and then it doesn't like say it over
Yeah.
here.
It prevents it from printing it out.
Yeah.
And no, that's actually one thing. Sometimes it's convenient to print things out, but if you're trying to do a lot of math, printing out something, especially within the system dynamics, because OD45 runs that function a lot, and printing is really slow. So if you're printing things out within your state dynamics function, it'll really slow down your code.
Yeah. Wait, also, I realized I made a mistake here. It's all over M. That's better.
Oh, yes, you're correct.
Okay.
So yeah. So now with having the M in here, it can be a little bit more convenient since now you're not passing. So now you're not passing that as an argument.
Okay. So, I can just do X. Also, I saw that when you made your column vector, you don't put semicolons and you just create new spaces for all them, and that works the same way.
Yeah. So I like doing that because I think it looks pretty looking like a column vector, and
Yeah,
you
it
don't.
does look like a column vector.
If you have it across those multiple lines like that, you don't actually need semicolons. You can put semicolons, but it's not required.
Okay.
So that's another example of Matlab having a million different ways to write the same. There's so many different ways to define just a column vector because you could also do like a row vector and then transpose it or something.
Yeah, transpose
There's
it.
a lot of ways.
Okay.
So now we could basically go through your equation for x dot and fill this in.
I have to write v sub x as a function of either t or x now.
Yes. So v sub x, that's a part of your x.
Yes.
So you see which element it is, what number it has.
That is this one.
Yep.
So x parentheses 3. X not.
Correct.
X, yeah, x not.
Oh, so it's just x.
X?
Yeah. So in
But
here.
it's called x not, though.
Wait, are you saying x naught or x dot?
Not.
Oh, okay. So within,
Right?
so when we're within the function, we don't have access to that x naught. We're basically in a new script with completely different variables.
Okay.
The only variables that we start the function, basically, think of it as its own script. The only variables in the workspace, so to say, are the inputs we give it.
So like any variable like right here or like right here,
Yeah, so
after and it won't know.
basically, if we go into that function, it's as though x naught doesn't exist. You can't call it, you can't access it. And there are ways of, getting around like that, like making x x not a global variable that can be accessed anywhere.
Yeah.
But that can lead to, a lot of, dumb mistakes. Basically, the technical word for this is scope. Scope is basically, what level of stuff you have access to. So a function has its own local scope. There's a global scope where all your global variables exist. And, yeah, basically each function gets its own scope. So it's nice and independent. And, keeping track of the scope can, lead to some, that helps you keep all your code nice and contained and, segmented. So yeah. The function basically does its job and then it returns the variable, and any information in the function that wasn't returned is just gone. But that's fine because we just need the function to do its job. All right, that's looking good. So now we get to the fun ones.
So this one would be time times cosine of x5.
That's correct.
divided by m.
Yeah, and
Okay.
so the deal with this is because we have m in here, if we try to access m somewhere else in the code that's not in this function, it doesn't exist.
Got it.
But in this case, we don't need to do that. So which method you use of passing m to the thing, whether you just have it inside or whether you have it as an argument, that kind of depends on whether or not you need m in other places.
Right.
10 times m.
It won't like 10m.
Yeah, MATLAB, you need to explicitly use the times. Because
Okay.
otherwise they'll just think you're trying to say like variable 10m, and that doesn't make any sense.
Okay.
I don't even think that's a valid variable name. MATLAB will just get angry at you.
Okay. Otherwise, is this line correct?
Yeah, that looks good.
Okay. And then last, we have to do the scary one. So that'd be sine of x of 5.
Well, so that's sine of t, not sine of theta.
Oh,
Yeah,
that's even easier. Sine of
nice and simple.
times cosine of t. And then divided by absolute value of sine of t.
All right. So now, real quick, don't forget to put a semicolon on your x dot because you don't have that right now. You can see the equal sign has a warning on it just to.
Got it. Okay.
So now you can go do OD45.
So you do it after end?
So the one thing that I think is a little weird, MATLAB requires that anytime you use the function, all your function declarations using the function keyword have to come at the end of your code. So you can't put any other code below it, other than more functions. That is, you can have as many functions as you want in the file,
So the
but we have to
declaring
put,
a function has to go at the end.
yeah. And
I feel
basically,
like that doesn't
once you
make any
declare
sense.
that function, that can be used anywhere else in your code.
I feel like that doesn't really make any sense.
Yeah, I don't really like that it comes at the end.
It just makes more intuitive sense to define your function first and then do stuff with it later.
Yeah, that's how it is in Python, where Python you usually define all your functions and then your main code that you run is at the bottom. But MATLAB is contrarian.
Okay. So in this case, we have the output t and then x,
Correct.
and then equals
Yeah.
e.
And now because we don't have any weird input arguments, we could just provide just the function handle. So that's the at system dynamics.
Is that what ODE fun means?
Yeah, so ODE fun is basically shorthand for ODE function. Usually when you see fun in a like argument thing, that's typically shorthand for function.
Okay. And just curious, why at?
So basically what at does is that's telling MATLAB, rather than calling this function, I want a reference to the function so that I can basically make a, basically the calling that at basically making a variable that is just pointing to where the function is so that you can then pass the reference to other code, and then that code can say call whatever function that this variable is pointing to using these arguments.
Okay.
We're basically telling it's basically a good way of just giving MATLAB a way to execute our code.
Got it.
So actually, in this case, because because we're not doing an anonymous function here, you don't need those input arguments.
What do you mean?
So the parentheses after your system dynamics in OD45, you can delete those.
Why
Yeah.
don't need them again?
So uh, in the example I was doing on the previous page, uh, I had system dynamics with 3 arguments, and that's not compatible with OD45, which only accepts exactly 2, t and x.
Okay.
And so that's what I was doing there, where I had an anonymous function that basically wrapped around my other function. But I don't need that here.
Okay.
Essentially, the reason you don't need that t comma x putting in the arguments within OD45 and the problem we're doing right now is because we're not calling the function there. We're basically just telling MATLAB this is our function. Use this. And later on, if you were to look at whatever code runs OD45, wherever that is, it then in there does the work of doing that OD fun t comma x. It puts in the arguments itself.
Okay.
That's what's going on under the hood.
Mhm.
So now we need our time span.
We can do like first 10 seconds.
Yeah, sure.
Is that is
Yeah,
this
that's
a
correct.
column vector
Uh,
or a row?
I think I usually do a row vector, but I think you can do either or. I don't think it matters.
Okay.
Um,
It's also
yeah,
row vectors is you can do a space or a comma, I believe.
yeah, both work.
Okay. And afterwards, want x naught.
Yep. Then you just
Okay. Oh,
provide
so
x
that's
naught.
how it solves the like the equation with the
Yeah,
initial variable. Okay. And then options is whatever.
yeah. Options. That's not something we need to deal with right now. When you get to like really hard problems, sometimes you need to mess with how OD45 behaves, and there's a number of different like settings you can tweak with it to get it to run better, or sometimes it doesn't work at all. You need to mess with things.
Hmm.
Um, there's some equations that OD5 won't work on, and then you need to use a different ODE solver. There's a number of different ones like OD15S, OD23. I don't remember all of them. But for the most part, OD45 is the most powerful one and is applicable in most situations.
Hmm.
Basically, try it with OD45, and if it breaks or doesn't work, then you could start looking at other options. So now, let's do
Did you
some
see
plotting.
how? Did you see what x had?
Ooh, looks like we got a nan somewhere. Um, oh, you know what? Are we doing is sine of t just returning 0 and then whatever divided by 0 becomes nan and then that just propagates through? That's probably what's happening.
Sine of t where?
Well, so see the equation for theta?
Yeah.
If t equals 0, then uh the entire sine of t, if t equals 0, is also 0, right?
Yes.
And then whatever divided by 0 is not a number. And then because theta is not a number, the v is not a number, and because v is not a number, p is not a number.
Ah.
So let's okay. So I think the maybe the right answer here would be
Let's just
to
start at
change the
second equal 1.
equation, but I'm thinking, yeah, let's just do that. Just change it to 1.
Okay.
All right, does that there we
Yes.
go. Does it eventually go to nan? Okay, no, it doesn't. Perfect. So what we can do now, um, here we go, and
Plot it.
let's graph it. So let's first just plot a top-down view of how it's moving. So do you want to plot the x position versus the y position?
Wouldn't that be like a multivariable function?
Well, so we have a vector of all of the x over time and a vector of the y over time.
Right.
So do you know how to
Like combine them both.
yeah, so we have all of that within one big X matrix. Do you know how
Yeah.
to extract a particular vector from that?
I saw that you did it using this.
Yes. So do you know what that syntax means?
It means every single thing in the row and only first column.
Yeah. So every row, first column. That's correct. You
Yes.
got that right.
But how would you do it so that
It's X position versus Y position.
it can just do it? I feel
Yeah,
like
you could
wait.
just. What was that?
That doesn't really make sense to me.
Well,
But
so think
let's see what
about.
happens.
Well, so you can't do Y. Y isn't a variable that
Oh, right,
exists.
X.
There you go.
Oh,
Look at it go. It's mostly falling, but going to the right, kind of as we expected. Um,
why don't we
okay.
extend it to like 100 seconds? Oh, that's boring.
Yeah,
I was hoping it'd make a shape or something.
maybe it would be more exciting if we changed theta. Okay,
Yeah.
let's finish graphing and then we could try and make it exciting.
Okay.
Um,
Um,
so yeah, then do you also want to plot Vx?
yeah.
I'm sure Vy is going to be really lame, but Vx might be at least a little interesting.
Vx would
Yeah,
be
and then maybe as a last thing, plot theta.
yeah. The 3, I think. Okay.
All right. Did you run that? Or is
Yeah,
it
it's
just...
right here.
Oh, so that's your... Is that theta?
That's Vx.
Oh, that's
To
Vx.
expected time.
Oh, okay. That's also not very interesting. So this is a case of
You can find a more
the free
interesting
body
example.
diagram looks exciting, but the actual motion of the block is eh.
Okay.
Oh, you used a colon instead of a
Oh.
semicolon.
Oh. Oh.
There we go.
Wait. Why does it progressively just start increasing?
What was that?
Why is theta progressively increasing?
So, if you want to scroll back down to there, I'm not 100% sure if this is what's going on, but I'm going to use this as an excuse to talk about it anyways. One of the things you'll notice with OD45 is, if you recall, it's an estimation.
Mm.
So oftentimes you won't get perfect answers.
Yeah.
So what I'm guessing is going on here, we might have an issue somewhere else that's causing this.
It's
But
also all negative pretty much when we asked for an absolute value.
okay, I'm thinking maybe we just...
Right, but this
Well, how
should
is
look
it?
like this should be exactly a absolute sign value.
Well, Kimai is the derivative of a absolute sign value. And sometimes sometimes the derivative of absolute value of sign is not necessarily always positive, because it goes up and then down and then it goes back up again, you know?
Mm-hmm.
In any case, because it's an estimation, we don't get exactly the right answer. And you can see it's only varying a little bit.
Yeah.
Because if you look, it's only going up like, a small fraction. So like over 1,000 seconds, it only goes off up to 1. Um,
But no, this is actually correct because it's absolute value. Oh wait. Oh, whoa.
oh, what the hell? Oh, that's the path. Okay, I thought that was a... So I guess after a really long time, it starts doing something weird.
Yeah.
That's interesting.
No, but look at this right here. Okay, maybe I'll bring it to 1500.
Oh,
It does exactly what it's supposed to. It does do absolute value of sign. It starts out negative, but then it like flans out at where it should be from 0 to 1.
hmm.
So this is correct. It was just wrong in the beginning, I guess.
Well, actually, no, it should be going negative because the derivative is
No,
not
no, but
always necessarily positive.
But this is plotting data, and data is
Oh, I'm
we
a
know
fool.
data.
You're right. It's
Data is
plotting.
absolute
Yes, you're
science.
you're
So
right. You're
this is
right. I see what
exactly
you
how it
mean.
should look like.
Yeah. So
Although it does do some interesting stuff afterwards. Oh, wait, wait, wait. Okay. Huh.
yeah, seems to me like this might be some funky numerical thing. Um,
That's cool.
okay. Well, in any case, there's one last topic I would like to cover today. So
Okay.
before we go on to that, do you have any more questions about any of this stuff?
Not really. I
Yeah,
think.
I guess also I'd appreciate if you could save that and send the file to me.
Yeah.
And then just DM me this because I don't want Abby to look at it yet because I want to make her do it.
Okay. You got it. I'll send it to you
Yeah.
after you
No,
finish.
why don't you just do that after so we can
Yeah.
fit this within our time? So do you want to stop screen sharing?
Yeah, I can do that.
All right. So now I will share content Windows. All right. So what I have here, this is a handy website I came across quite a while ago. Um, this is basically this whole website is just filled with controls challenges. And basically what we have here, we have a little block, and I believe that this is a very simple example where there's just it's basically just sitting there, and we're applying some force on it. And so we're going to get into some actual control stuff. Basically, the way the site works is we get a function for returning the control input, and then we can return whatever we want. And right now, it's returning a sine function. But let's say I want to do something else and return 5 so that the force is always 5 if I run this. Oh, do I have to restart? There we go. It just scoots off forever. Um, Basically, we're defining the force. The goal of this is basically for this example, we want this block to go to exactly this position defined by the arrow. Um, so in order to actually do that, one of the simplest ways to do any kind of control is called proportional control. And that's basically what we're going to use right here. Essentially what we're going to do, we have the block position, block.x, and we know we want the position to be here. So what we're going to do is just make the force proportional to how far away we are. So the farther away we are, the harder the force we have that will push us back. So I'm just going to make this minus. The traditional thing is to use K, which is the gain, where, you know, that basically defines how hard of a K equals 10. Oh, by the way, this is JavaScript, which is kind of awful, but that's just how the web works because this is a web app. um, so basically what this will do, this says, I'm actually going to make this lower. I'm just going to make this 1 for now. This will basically say, take the distance you are from the position or from the target and take the negative of that and multiply it by k. And so what will happen now if we run it, you can see the force gets larger and then smaller as we get close, and we overshoot it, but then because now the distance is on the opposite direction, it flips the control input around and we go backwards. So what's going on here kind of making sense?
Uh, yeah. So if you increase K,
What happens if you increase k?
could you potentially overshoot and never miss it, never get it?
Yeah,
Or
so if we restart it, now it's much more aggressive and it overshoots harder. It goes back. So there's kind of a when you're doing this, there's a balance here.
Yeah,
You want
so
to pick a K
there should be
that's
an ideal K that would go as fast as possible. Like it would bring it back to
so if we choose something really small like zero point 0.1, I'm about to hit F5 like this MATLAB. With 0.1, it goes really slow. But once it gets there, it probably won't overshoot at all. Once it gets there. So yeah, you're right. There's a balance here. Um, and I guess uh, obviously the simplest way to do this, so you can see there's no overshoot. It's basically just going right up there. The simplest way to do this is basically to go ahead and just do trial and error, just try different Ks and just see what works really well. There are fancier ways to figure out what to pick for K, but I'm not going to go into that today since there's like 2 minutes left on our thing. If you want to go all the way to like the very fanciest end and pick the mathematically optimal K, that gets you into, optimal controls territory. And optimal controls, I actually just took Kalagi's grad class on that. That's a exciting one. It's actually, you know what? Let me quickly, as a final bit for today, I will share a map of controls just to kind of, here we go. This is a nice graphic I found online that's just a map of control theory. Have you ever seen something kind of like this?
yeah, I have.
Yeah. So if we, where's what we're doing? So state estimation. Wait, no, that's not what we're doing. We're basically doing modeling and simulation. So we're kind of doing linear state space stuff. Um, I guess technically the modeling method we were using was for nonlinear state space, but if you remember, we learned about how to write a linear state space. Um, the feedback we were doing, where's that at? We're proportional control is right up here, part of this PID section. And we'll learn more about the rest of PID in a future lesson. But you see it's kind of little bits. Optimal is way up here. This is finding, absolute best possible type practice. Um, yeah. So for the most part, we'll probably stick mostly in this, linear area and modeling and simulation. I don't know. Might do a bit of system analysis, but there's a lot of stuff to do. Um, yeah. So any last questions for today?
Um, I guess is how will we be using something like ODE 45 um into something like where we could apply controls?
So, bit of a sneak peek at what we're going to do next time. So, kind of as you just saw with the example I was doing on that website where we're finding a K,
Mhm.
essentially what we're going to be doing in MATLAB is now within our controls, that our control input is going to be an element of our state dynamics. So there, or not necessarily an element, but there's going to be, U's that affect some parts of the state dynamics,
Right.
and
That's
we'll,
like our force function and theta function, right?
yeah. So maybe, as an example, let's say in the future, theta, rather than being, you know, t- uh, have an equation that depends on time, our theta might instead be a control input. So we have U of t equals theta. And now that's no longer a state variable that we have to keep track of, but now anytime we have theta in our equation, we get to pick it. And we could pick whatever theta we want. And within that OD45 function, we can, put in our algorithm for picking, u, or theta in this case.
So pretty much, like, would you say that whatever function we're going to use in the future, like at every second, it pretty much decides what to set like your force and your theta equal to.
Yeah, so
Like it's the path
at
that predicted to make.
yeah, basically what's going on is you have your at any given moment, we have our state space. It's a point in, all the possible states we could have. It has a position, velocity, etc. And at that point, we kind of what we were doing today, the system dynamics are, at that point, there's a set way the system dynamics are moving. We know the derivative, so we know, how the system dynamics are changing. Additionally, at that set point, this can actually, you know, change to where it's not necessarily always exactly the same. But at any given point, we can also write a algorithm that picks a u depending on what that point is.
Hmm.
Um, and that's kind of where we get that k. Uh, Basically, what we're saying is, if we're at this position in the state space, k should be this for this value, or sorry, not k. K is a constant. My bad. This value of u. So actually, yeah. So for a particular value of u, um, that will move you towards your desired goal. And basically, you saw it in the web thing. Our end goal was a particular space along a line. But our end goal, that changes depending on the context. Maybe our end goal is to have our car driving at an exact set speed with cruise control. Um, or, for the Falcon 9, the end goal is it wants to be at rest at a particular position on the landing ship. Does that kind of make sense? The idea?
Yeah,
Okay.
I'm
Um,
just a little confused, but like, this how does like the computer decide?
yeah. So the way the computer decides u is kind of what we're going to be getting into. There's a lot of different ways that you can pick u, and some work well for some problems and some don't work well for others. And kind of what I was, showing you with that, k, that's a very simple way to pick u. Basically saying u is proportional to how far away you are from your goal.
Okay, yeah.
Okay. Any last things?
No, that's it.
All right. Yeah. So in the future, we'll get more into doing some actual pancake. I'm gonna stop recording and